when we have three molecules, A, B, and C. And this is the system that was done by our student Maria, who is a mentor here at the course. So we have a trivalent molecule A, tetravalent B, and pentavalent C. And molecule A can bind on two sides to B and on one side to C. B can bind to three sides on A and on one side to C. And C can bind on two sides to B and on three sides to A. So this is may be considered as a molecular dynamical system, but in network-free simulation, it's purely stochastical description that doesn't account proximity, doesn't account for whether certain molecular configurations can exist in reality, but just basically you think that each of these molecules is infinitely flexible string with bits far enough so each side can access any other side. So unordered regions or RNA with multiple sites is a good representation of those molecules. And as I said, usually these systems, there is no other way to approach them as with molecular dynamics, how they can form complexes. Because if you think about, there is an infinite number of possibilities how they can form. So A can bring two molecules B and one molecule C. Each of the molecules B can bring more molecules A, say this one sits here and there are two more molecules A and then C and so on. So this system is basically ununderstandable by a human being. What will happen if you start messing with these molecules? And network-free simulation provides a way to analyze these systems. And this analysis is pretty time efficient. It's very time efficient compared to molecular dynamics and even compared to spring salad that was discussed today. And this spring salad is already much more efficient than molecular dynamics because it coarse grains sites into spheres. Here you don't consider any diffusions, you just consider regular probabilities. So you have interactions. A binds to B, and here is B1 binds to A1, here is B1 binds to A2, and here is another tricky rule. So what's the difference between this one and this one? Here, two molecules A and B that are already bound some way, so they're already in the same species, they're already in the same molecular cluster. They can form extra bond. So these two molecules A and B are already in some large cluster. So they are not connected directly, although they may be connected directly. But maybe there are 15 more A, B's, and C's, and they are connected through them. So they still can form extra bond if these sites B1 and A2 are available. And here, this plus signifies that these two molecules are parts of two different clusters, of two different molecular complexes. So again, this one can be either individual A, or it can be part of a huge cluster that maybe it has all the sites being saturated with internal bonds, but accidentally this B1 becomes available. And network-free simulation gives you a way to simulate bindings, unbindings on these molecular interactions and track what's going on. Stochastically, you start with certain initial number of particles, or like concentrations. So this is 300, 200, 300 of trivalent, 200 of tetravalent, and 100 of pentavalent molecules. So something that, okay, I will repeat it later, but just regular stochastic deals with particles, but regular reaction kinetics deals with concentrations. And virtual cell has a way to convert on fly between number of particles and concentrations. So it goes like that, just by switching this button here. And this conversion goes, so you see now it's a bit numerical error. So it's 300 now converted to 299,999,999. So this conversion goes through the volume that is defined here. It's in this case 1 micrometer cube. So when dealing with stochastics, it's very important to track all the three parameters: number of particles, concentration, and volume. Because if some of them don't make sense, then your whole simulation, whether it's stochastic or even when it's deterministic, they don't make sense. Because if you do it in a very small volume, where like less than one particle may come, or if you do it with a very high concentration, or if you do it with a low concentration, so on. And in virtual cell, this conversion is, so say, for example, you have a number of particles 300. You switch to concentration, you see that concentration is okay, but your number of particles is kind of too low, and you will have a very, say, like something like that, and it runs fast. But this is not impressive. You don't understand the trend. In this case, you can go here. So your concentration is still fine. You're happy with the concentration. So you go into geometry and you switch 1 micrometer to 10 micrometer. Now you go back to specification. And now your number of particles is 3000 instead of 300. So we don't want it. So we go back, we want to keep concentration. So we switch to concentration. We go back to geometry. We switch it to 1. And then we go back to specifications. Concentration still the same. Number of particles came back to 300, 200, 100, something that we wanted. Okay, so I deviated from my main task, describing interactions between these three species, three molecules. So you cannot imagine the network of individual species that describes all the different interactions. So therefore, it's stochastic agent-based simulation, and the results of the simulations look like that. So first of all, you have observables. Observables is something that tell you certain aggregate quantities of your system. Say this is observable that tells you that what will be the count of all A's that an aggregates of more than 10. These will tell you what will be the count of all A's that an aggregates more than 3. These will tell you what's the count of all A's that an aggregate more than 100. And then you can do something like you can say what will be the number of molecules that have A, like 3 A's, 2 B's, and 1 C being fully connected. So this is, again, you want to investigate these clusters, and the way to investigate them, because you cannot just look at all species in transient at all times, it's too much information, is to ask questions. And these questions are asked via observables. So any questions so far? Okay, yeah, because I don't see chat. So if you want to ask questions, feel free to interrupt me and speak up. So now we get into simulations. And in simulations, the questions that we are all interested in, and like Oni and Les talked about it in Spring Salad talk, what will happen to this system? What are, for example, ranges on KF and KON and KR, the binding and unbinding rates, that they will form one single huge cluster, or they will form multiple small clusters. And if it's one large cluster, then whether this cluster is fully saturated, meaning that all sites are taken, or those clusters have like pretty sparse, a lot of sites. And if you think about it, like you may think that the more is a binding rate, the more cluster will be saturated. But in reality, it may be not so, because it may be that small clusters will just saturate themselves and they will not be able to form a large cluster. So this is something that in molecular dynamics would be very slow. In NFCM, it's still not immediate, but pretty easy to investigate. Like it takes, I started simulation about half an hour ago before I started to speak, so and it's a very large time. So anyway, let's see what stochastic results look like for this agent-based simulation. So this is a pretty small time. And at small time, we have 17 different clusters formed out of 600 molecules. And here comes, so this is a single run. It's completely non-representative because single run just stochastic gives you some results. So to analyze it, you need right now currently download this file, and this file may be downloaded for yeah. So for local runs, it's stored at your local system, and we actually can go and look up there users. So what Oni was talking about, yeah, we need to go into. So what Oni was talking about, so sim data temp, guess my temp is huge. No. Okay, so these are outputs that you're interested in. Okay. So this is distribution of all clusters at the final time point. And we have a collection, Oni has a collection of Python scripts that do analysis, both for Spring Salad and for NFSIM, and analyze those outputs. But for the simple case, you just can look up here at output species here in the no, this is not the right one. So let's look at this simple one. So there are only 17 clusters, and there is a single small one, and then there are so visualization here is a bit lacking. We are working on it. So this is a cluster of 200 molecules, and this is smaller. Somewhere here, you probably can find a cluster larger. Did I accidentally found just the largest one? Oh, no, this one is the largest. So, and even the largest cluster, it's not completely saturated. So this molecule C has a still available site for A, but it's almost saturated. So you can see that it's almost saturated. Yeah, you see this, this is connectivities between sites. So it's almost saturated, and still it's there are 17 clusters. Some of them are huge, some of them are 200. So the question is, what's going on? Why you have an almost saturated cluster, but it's not yet, it's not a single one. So, and then we can do like increase binding rate, on rate for, and see what will happen. And it's basically not increasing this cluster formation over same time, and then we can increase time and see what will happen over larger time. Again, what Les mentioned, that whether this cluster formation can be so like if you have a couple of large clusters, whether at some point they will click together. And so far it's not happening. So over a small time, it's still 50 seconds. You still have a large number. But then when you run it for a very large time, then you start seeing decrease in the number of clusters. So this is a system when we had less molecule. And then we have a, so let's see. Okay, so I don't have, so any questions so far? Again, please ask any questions. I don't see your, if any questions are asked in the chat window, I don't see it. So now how we can do multiple runs in virtual cell. So let me switch to another model that runs faster. And this model is a classical model, non-rule-based, not NFC model, when it's an oscillator. VLAR model when you have a RNA that can bind protein A and start mRNA transcription, which producing M, and then another site on this DNA, when A binds to it, it's producing repressor. So, and then this system behaves the same way as vodka Volterra, and it oscillates. So, when we do ODEs, then everything is very simple. So, it's having nice oscillation, and then you can do scan over over different values, so you can vary different. So in this case, we vary the size of the cell, keeping the same keeping the same number of molecules, and we can see that it oscillates. It continues oscillating. This is deterministic, continues oscillating, and then it stops oscillating. So at some point, you don't have enough molecules for oscillation. If you do the same stochastically, then the behavior is completely not obvious. So this is A. Again, here is nice oscillation. Here is nice oscillation. Here you don't know if it's oscillation or not, because it's already pretty low number, and whether it oscillates or not is not clear. So in this case, you do
Michael, you're keeping the number constant. You're just changing the concentration when you do that, right?
yeah. Well, I'm increasing the volume, so
Yeah,
I'm
so you're
increasing the
keeping the
volume,
number of molecules the
and
same.
I keep the number of particles the same.
Mhm.
So I am decreasing concentration. So in this case, you need to do parameter scan. Oh, sorry, multiple scans and multiple simulations. Multiple simulations are available here. So there are different. So whatever was done so far was a single trajectory. Now there is an important. So you can switch to multiple runs. There is an important part here which says random seed. And when you do multiple runs, default is random seed. But sometimes you would like to test, and then you can do customized seed. So in theory, multiple runs with customized seed that is the same should produce just a single trajectory. So I have it somewhere already simulated. So I can show you the smoothness. I can show you. All right, so it was a different model. So let me quickly open another model. So advanced, I will do just, so the easiest way, if you have a lot of model, the easiest way to find something is just to go like that. And you will see all the models that you did over the last few days. Yeah. Sorry, is it this one? No. Okay, so I can try to run it now for something simple. So let's do now. This is my system repressor oscillator. And I have 2 minutes, so please ask questions. Okay, so I would like to change here specification. I would like to go into geometry, and I would like to increase 5 times. So let's see. We have now specification, so the same number of particles, but concentration will be much lower, 5 times lower. So we go back to the number of particles, simulation. So let's switch it to 200 to make it faster, and we can run it locally. So far I'm not doing, okay, so this is my stochasticity. Now I can go here, solver, multiple runs, and let's do it, I can do it 100. 100. So something else, what you will see something that's still stochastic, because my output options are pretty sparse. So I have a 200 outputs every 1 second. And by the way, this is something else that is very important for stochastic simulations, that if you do output option pretty sparse, then you can miss any behavior, like especially with oscillation.